part 3, continuous time Markov chain. And we have 2 parts today. First, we will talk about what is a Poisson process. So the definition, basic properties, superposition, and characterization. And the second part is the introduction to continuous time Markov chain. Okay, and for continuous time Markov chain, we just give an introduction today. So we'll introduce what is the semi-group and holding time. And the next lecture, we will talk about the generator of continuous time Markov chain. And in the last lecture, we'll talk about the stationary distribution for continuous time Markov chain. So start with Poisson process. So we start with the definition of a random point process. A random point process is a countable random set of points of real line, which corresponds to the sequence of times of occurrence of some event. For example, we record the arrival times of customers. Then this arrival time gives us a random point process. So this is roughly speaking, and the precise definition is the following. So a random point process on R plus is a sequence of random variables Tn such that this is an increasing sequence of random variable. Second, it converges to infinity as n goes to infinity. So we can imagine that this Tn just record the arrival of this sequence of time, just record the arrival time of customers. So Tn corresponds to the nth customer arrives at time Tn. So this is a random point process. For this process, we define 2 notions. The first is called inter-event sequence. So by the name of this random variable, we see that it characterizes the time difference between 2 neighboring occurrences of the event. So Sn is the time difference between the arrival times of 2 neighbor customers. So this is called inter-event sequence. The next notion is called counting process. So counting process is defined in this way. For any interval a, b, we define NAB. So this is a definition for NAB. So roughly speaking, we see that we're just counting how many Tn's fall into this interval a and b. So this counting process NAB just counts how many customers arrive between time A and time B. And here, for this counting process, we have a few more words to say. So first, by the definition, because we always define an interval with open in left, but closed on the right. So this process is naturally right continuous. So if we define NT as the counting process from time 0 up to time t, because we define this closed in the right-hand side, so this process is naturally right continuous. And if we always define at the right-hand side is an open interval, then it will be a left continuous process. But in our lecture, we always restrict to the closed interval on the right, so we are considering a right continuous process. Okay, so this is the random point process. Now we can introduce what is a Poisson process. So a Poisson process is just a special kind of point process n with the following 2 properties. So Poisson process it is a point process n on the real line with the following 2 properties. First, the first property we call independent increments. So for this part, it means that for any time interval, so as long as the time interval are disjoint, the number of the counting process on this interval are independent. So this is makes sense in our real-day life. So suppose we're just counting how many numbers of customers arrive in this interval. Usually, when we are considering the time slots, then the number of the customers arrive within this time interval are independent with each other. The second property is we want to characterize what is exactly the law of the number of customers arrive in the interval A and B. So we require that this random variable satisfies the law of Poisson random variable with mean lambda times B minus A. So first, this Poisson random variable with this intensity, so this intensity only depends on the time length of the interval. So this is also reasonable because we are counting how many customers arrive within this interval, and it shouldn't depend on where we start and where we end. It only depends on how long this interval is. And second word, this intensity is a linear function with respect to the time length. Okay, and just a quick recall, what is a Poisson random variable? So for a Poisson random variable with such intensity, it means that this random variable, the probability for this random variable equals k. K is an integer, has the probability so this is the law of a Poisson random variable. So here, a Poisson process is just a special random point process with these two properties. The first is called independent increments. Second, we characterize the law of the counting process within this interval A and B. It has to satisfy a Poisson random variable. It satisfies the law of a Poisson random variable. And the mean is just linear in the time length of this interval. So this is the definition of a Poisson process. The first property we derived is about the property of the inter-event sequence of this random process. So consider we have a Poisson process, and Sn is the inter-event sequence. So Sn is just the time difference between two neighboring arrival times of the customers. And the conclusion is, if our random process is a Poisson process, then this sequence Sn, they are IID, and their law is exponential with parameter lambda. Okay, so this is the first property we derived for the Poisson process. So why this is true? So in order to show that the sequence Sn is an IID exponential law, we only need to check that what's the density function of this sequence. So for each one, it corresponds to an exponential random variable with intensity lambda. And if this Sn is an IID with exponential law of parameter lambda, then the density function of this sequence of this vector S1 to Sn should be given by this form. So if we prove this is true, then it shows that the sequence Sn is an IID sequence with common law exponential with mean lambda, with parameter lambda. So mean is 1 over lambda. Okay, so now we want to check what's the intensity function for Sn. But the only information from the sequence is we only know the information about the Tn, not Sn. So what's the relation between Tn and Sn? So we know that Sn is the time difference between two neighbor Tn. So if we want to write Tn as a function in Sn, then we know that T1 is S1, T2 is S1 plus S2, and Tn is S1 plus Sn. So in order to check that the density for S So in order to check the density for this vector S1 to Sn is given by this form, it is equivalent to check that the density for Tn Okay, so it is equivalent to check that the density for Tn is given by this form. So there is a one-to-one correspondence there between S1 to Sn and T1 to Tn. And here is the changing law. So to check the density for S is given by this guy. It is equivalent to say that we need to check the density for Tn is given by this density function. Okay, and then let us check what's the density for this Tn, sequence Tn. So we fix we want to check what's the density function for this T. So by the definition of density function, we know that this density function equals the probability that Ti is in the neighborhood of big Ti is in the neighborhood of small Ti, and then normalized by the length of this neighborhood. So this is the definition for density function. Okay, and then let us check what's the probability here. So now for this event, we're considering that the random variable Ti happens in this small time interval. So what this tells us, so first we know that T1 is between T1 and T1 plus epsilon 1. So this tells us up to time T1, there's no one arrives, so no customer. So the number of counting process equals 0. And then we know that in this in the time interval from T1 to T1 plus epsilon 1, we have one customer. And then between this time to the next arriving time T2, there's no customer. And then for the time interval between T2 and T2 plus epsilon 2, we have the second customer. And then no customer before T3. And then we continue. So we know that This is the Tn minus 1 customer arrive in this time interval. And then for the next time interval up to Tn, no one arrives. And the final event is Tn is in Tn, from Tn to Tn plus epsilon n. So this only tells us in the last time interval, we have at least one customer. So there's no restriction that they will have only one. So possibly there are many. So this last event only tells us from Tn to Tn plus epsilon n, we have at least one customer. So this is another interpretation of this event. And now we can use the property of Poisson process, the definition of Poisson process, to calculate this probability. Okay, so first, from the definition of Poisson process, we know that since all these time intervals are disjoint, so all these random variables are independent. And each of them is a Poisson random variable. And the intensity is given by lambda times the time length of this time interval. So what we know is the probability of this event then it's given by the product of all the probabilities that I listed here. So the first one, from 0 to T1, there's no customer. And we know that this guy satisfies the law of Poisson random variable. So this Poisson random variable equals 0. The probability is E minus lambda T1. So this is the probability for the first event. And for the second, so this random variable equals 1, and the intensity is lambda times epsilon 1. This is the probability of the second event. So this is the Poisson random variable equals 1. And then this event, so this Poisson random variable equals 0. The probability is so this is the probability for the third event. Okay, so for all this event, they have similar type. So we know that okay, so this is the event for the n-1 customer. So for these two events, this is the probability. And for the last one, so it corresponds to a Poisson random variable is greater than 1. And the probability is 1 minus the probability equals 0. Okay, so this is the probability of the last event. And now we rearrange this probability. So first, this guy and this guy, they canceled each other. And now consider this exponential. The product of this exponential corresponds to the summation of this exponent. And then it just cancels one by one. So finally, we will get Tn minus T1. And here is T1. So what we have is, for the exponential part, we have E minus lambda Tn. And for this part, we get lambda to the power n minus 1 times epsilon from 1 to n minus 1. And for the last part, is this one. So from here to here, just rearrange this probability. And now we can calculate what's the density. So now we need to normalize this probability by product of epsilon i's. So here we see that this is product from n to 1 to n minus 1. Here is the product from 1 to n. So they cancel for the first n minus 1 term. What we have is and now we let epsilon n goes to 0. So the last term will have a limit lambda. So this shows that the density function for T1 to Tn is given by this form. And it is equivalent to say that the density for S is given by the product of exponential laws. So this proves the first property. And here, just one remark. So before I prove this theorem, I give you the definition of Poisson process. But I haven't said anything about this definition, so why such a process exists at all. And so suppose that we have such a process satisfying this law, and we prove that for the inter-event sequence Sn, there has to be IID with exponential distribution lambda. So from this first property, this also tells us how to construct the Poisson process satisfy this property. So we can just start from a sequence of IID exponential law of IID with exponential distribution of parameter lambda, and then define Tn accordingly. Then this Tn will give us a process satisfy the property here. So on the one way, you can see this is the definition and this is a property, but this property also tells us how to construct a process satisfy this definition. Okay, so this is the first property. The second property is called Markov property. So Markov property, so the Markov property says suppose this NT is a Poisson process. For any fixed time S, we consider a process NT plus S minus NS. So this is a new process indexed by positive real. And the conclusion is, for this new process, it is also a Poisson process with the same parameter. And moreover, it is independent of what happens before S. So this is called the Markov property for Poisson process. And in fact, the proof is just immediate from the definition, because we know that this NT is just a counting process of the Poisson process. So we know that NT plus S minus NT corresponds to exactly the number of the customers arrive within the time interval T to T plus S. And from the definition of Poisson process, we know that this random variable satisfies a Poisson random variable with intensity lambda S. With lambda T. And for this new process, we can also easily check that it satisfies the independent increments. So for this new process, it is also a Poisson process with intensity lambda. And also, of course, it is independent of what happens before time s, because this nu is the counting process, is the number that how many customers arrive within times between time 0 and u. And we know that this time interval is disjoint from this time interval, so the two random variables are independent. So the new process is independent of what happens before time s. And this is called Markov property of Poisson process. We will talk more about Markov property when we introduce a continuous time Markov chain. So first, you see that the Poisson process satisfies Markov property. So later, we will also show that Poisson process is indeed a continuous time Markov chain. Okay, second property, and then let us check the third property. It's called the superposition of Poisson process. Okay, so now we want to consider a family of independent Poisson process. And we want to take the sum of all this process. And the conclusion is the summation of all independent Poisson processes is still a Poisson process. Superposition. So it says that we have a family of independent Poisson process. And for the Poisson process Ni, the intensity is lambda I. And the first conclusion is the two distinct processes in this family have no points in common, so they can't. It is impossible that the two processes jump at the same time. And the second conclusion is, so the first results I won't prove during the lecture. You can check the proof during the lecture notes. Okay, so for the second conclusion, it says that if the summation of all its intensity is finite, and we denote it as lambda, then we define a new process NT. So it's just a summation of all this Poisson process. The conclusion is this NT is also a Poisson process. And the intensity is lambda. Lambda is the summation of all these lambda i's. So this tells us the superposition of independent Poisson process also gives us a Poisson process. So this is also can be considered as if you have two windows, and each window has counts how many customers arrive. And then these two sequences will be independent of each other. And if you put them together, so now you consider the the collection of two windows and count the number of the customers arrive, then this is still a Poisson process. So there's no difference if you consider them separately or put them together. Okay, so why this is true? So first, if we define this process, so first of all, this process is well defined because we know that for I and t, this is a positive, non-negative integer. So of course, we can define this random variable pointwise. So because this summation in the right-hand side, if we stop at n, then this is an increasing sequence in n. So we can define this limit pointwise. So NT is well defined, almost surely. And because we know that each NTI has independent increments, and for different I, they are independent. So it is immediate that this NT also has independent increments. So in order to check NT is a Poisson process, we only need to show that. So only need to check we only need to show that NT has the law of Poisson random variable with mean lambda t. So we only need to check what's the law of NT, because we already know that it has independent increments. So how to calculate the law of NT? So we know that NT is the summation of NIT, and each NIT is a Poisson random variable. So we start from two random variables. So suppose we have two random variables, x and y, they are independent. Independent Poisson random variable. And the first one has intensity lambda 1, the second one has intensity lambda 2. The first conclusion is, then x plus y is also a Poisson random variable. With intensity lambda 1 plus lambda 2. So why this is true, we can check it directly. So we need to calculate what's the probability that x plus y equals n. And then we divide this event according to the different value of x. And since x and y are independent, so this probability equals the product of these two probabilities. And each x is a Poisson random variable, and y is also a Poisson random variable. We know that the probability here is and the probability for y and here, this 2 exponential has nothing to do with this summation. So we're just summing over the product of this guy and the product of this guy. And this is a well-known formula that if we're summing for k from 0 to n, this equals so this tells us x plus y is also a Poisson random variable with intensity lambda 1 plus lambda 2. And from here, we know that because each NIT is a Poisson random variable with intensity lambda IT. And if we take a finite summation, the above analysis tells us the finite summation has to satisfy the law of Poisson random variable with intensity is the summation of all. And now the only problem is how to pass the limit for n to infinity. So we know that NT it is the limit of this, it is the limit if we take this n goes to infinity. Before we're taking the limit, we know that each guy is a Poisson random variable with intensity with a known intensity. So now, how to pass to the limit? So first, by monotone convergence theorem, we can take expectation of NT. We know that the expectation of NT equals the summation of the expectation of NIT. So this gives us And because we assume that the summation of lambda I is finite, so this is lambda t, and it is finite. So first, we know that this NT is well-defined, and it is also finite almost surely. So because the expectation is finite, we know that this random variable is finite almost surely. And since it is almost surely, we know that NT is the limit of this sequence. And for this sequence, each guy just take value in positive integers. So the taking value in positive integers. This tells us if this NT is finite almost surely, it must coincide with some n. So we know that the indicator function such that we cut off at n. So this guy equals k has to converge almost surely to the indicator function nt equals k. So this is because all this process just take a value in positive integers. Okay, so then we can use dominated convergence theorem to conclude that the probability so now we are taking expectation to both sides. And since this is just an indicator function, it is bounded by 1. So by dominated convergence theorem, we know that this probability will converge to the probability of nt equals k. And for this finite summation, we already know that it satisfies the boson law of with parameter lambda, with the right parameter. So we know that the left-hand side, the probability of this event is so this is the probability for the left-hand side. And we know that we have convergence to the right-hand side. So this implies that the probability in the right-hand side has to equals and this tells us it is true that this NT satisfies the law of Poisson random variable with intensity lambda t. So this proves that the superposition of two independent Poisson process is also a Poisson process. So this is the superposition of Poisson process. And the next property is also about this superposition. So now, assume the same notation as in the first theorem. So we assume that this and I are independent Poisson process. And each one has intensity lambda I. And we assume that the summation of lambda I is finite. And from the above theorem, we know that this new process is well defined and it is finite almost surely, and it has the law of Poisson random variable. It's a Poisson process with intensity lambda. So now let us consider what is the first event time of this new process. So we call Z is the first event time of n. So this says that z is the time of the first customers arrive in this new process n. So precisely, it means that if we denote for one Poisson process ni, if we denote in as the time sequence for ni, then this z just is the first of this T1i. Because z is just the first event time of this new process, so it corresponds to the minimum of all these first events for different process. Okay, so this is z. And another notion is called j. So j is the index of the Poisson process responsible for the happening of z. J So suppose that we only have a finite number of Poisson processes. So suppose everything is finite. And then we define the corresponding first event zk. So zk then is just the minimum of the first event time. And then the corresponding jk is just the index that it happens at which process. So it is the index such that, so jk equals I, it means that zk equals ti1. So jk is just the index of the process that it is responsible to the first occurrence among all this process. And we can also define for, if we have an infinite sequence, then we can also define j as the limit of this jk as k goes to infinity. So this is the random variable z and the random variable j. And the conclusion is these two random variables are independent of each other. So first, we assume z is the first occurrence of is the first event time of the new process. So in fact, this conclusion is very anti-intuitive, because suppose we know that the first event I is responsible to the first occurrence. Then if this process I has a larger lambda I, then it should tell us it happens quicker. But the conclusion here is, no, they are independent. So there's nothing to do with these two random variables. So no matter which process is responsible for the occurrence of the first event, the occurrence time is independent of this index. Okay, conclusion. J is independent of Z, and we can explicitly calculate the joint law of these two random variables given by this formula. Okay, so why this is true? So we first prove the conclusion for finite case. So now we consider we only have finite number of Poisson processes from N1 to Nk. And we define Zk and Jk correspondingly. So Zk is the first event time, and Jk is the index of the process responsible for this first event. And then let us check what's the law of these two random variables. So first, what's the law for zk? If zk is greater than a, we know that zk is the minimum among all this first occurrence time. So z is greater than a. It means that all of them greater than a. So all of them has to be greater than a. And we know that this k process are independent. So of course, this k times are independent of each other. So it equals the product of the probability. And for each process, we know that each one is a Poisson process. So each time ti satisfies the law of exponential with intensity lambda I. So the probability for exponential is greater than a. It's e minus lambda ia. And then we write the product in front to the summation in the exponent. It equals this. So now we already know what's the law for zk. And then we need to check what's the joint law of zk and the jk. Okay, joint law. So we want to calculate what's the probability that jk equals 1 and zk is greater than a. So you can change this index 1 from 1 to k for any other index. So, and the procedure is the same. You can calculate the probability. So it equals 1 or it equals I. There's no difference for the calculation. Okay, so I will just fix this I equals 1. So what's this event tell us? So it tells us, so the first event time happens at the first for the first Poisson process, and we know that it is greater than a. So if we define this sequence is the first occurrence for different process from 1 to k, then this event is equivalent to say, so T1 is the smallest one. And it is smaller than the minimum of the remaining k-1 process. So if I define U as the minimum of the another k-1 process, then this event is equivalent to say that T11 is the smallest one, so it is T11 is smaller than U, and it's greater than A. So this corresponds to the first event time is greater than A. So these two are exactly the same event, so they have the same probability. And now let us check what's the probability of this event. So we want to calculate the probability of this event. And here, U is the minimum from the second process to the kth process. And because the process N1 to Nk, they are independent, we know that this U is independent of T11. So now it's just they are just the two independent random variables. And we know that T11 has the law of exponential with parameter lambda 1. So now we can just write out this probability out. So the density for T11 is lambda 1 times exponential minus lambda 1x. So this is the density for T11. And now we are calculating the probability that U is greater than x. So here we can just write out explicitly what is this probability according to the density of T11. And here for this event, so U is greater than X. We know that U is the minimum from 2 to K. And from the above calculation here, this is just corresponds to ZK is greater than X, but this K is the minimum from 2 to K, not 1 to K. So the calculation is exactly the same. So this one has the same form here, just the only difference is from 2 to K, not 1 to K. Okay, so now we can just do the integral explicitly. So this integral gives us and here we already know that this part equals the probability of ZK greater than A. So this part corresponds to JK equals 1. So because if you just put A equals 0, you will get that JK equals 1 equals this guy. So this tells us that this JK is independent of ZK, and the marginal law for ZK is exponential. And the marginal law for JK is just according to the ratio of the intensity. Okay, so this tells us, so the first occurrence of the superposition of Poisson process is independent of the index of that which process is responsible for this first occurrence. So, okay, I haven't taken the limit. So here we just complete the proof for finite case. So now we need to take the limit. So it's also true for infinite sequence of the Poisson process. So next, for infinite case, next we will take the limit as k goes to infinity. What we know is this event, jk equals 1, zk greater than a. It decreases to the event that j equals 1, z greater than a. Because here we can see that zk is decreasing in k because you have more and more, and then of course the minimums get smaller and smaller. So this event is decreasing to this event. And then we know that the probability of the left-hand side is already calculated, and the so this tells us the probability of the right-hand side. Is just the limit of the left-hand side. And this probability we already know. So it is this one given by this formula. And now we let k goes to infinity. It will give us lambda 1 over lambda e minus lambda a. So this also tells us this conclusion is also true when we have infinitely many process. So z is independent of j. And we also know the marginal law of each of them from this formula. Okay, so this is superposition of Poisson process. The last theorem we talk about the Poisson process is characterization. So what is the probability to characterize the Poisson process? So from the definition of Poisson process, we know that if we want to check a process is a Poisson process, we need to check two properties. The first is it has independent increments. The second, for xt, for each t, xt has the law of Poisson random variable with intensity lambda t. And this theorem tells us, in fact, it is easier. We have a much easier way to check whether it is a Poisson process. So the conclusion is the following three statements are equivalent. The first statement is the process is a Poisson process. So the following three statements are equivalent. First, the process is a Poisson process with intensity lambda. The second, xt has independent increments. And we have an estimate for the for the difference between two times that the difference is epsilon. So the conclusion is we only need to calculate what's the probability that from t to t plus epsilon, there is a zero jump. So the probability should decay like 1 minus epsilon times lambda times epsilon. And then the probability for the process that between t and t plus epsilon, there is only one jump. The probability decay like lambda times epsilon. So this is the second conclusion. So here we can say that to check these two probabilities, it's much easier to calculate explicitly what's the law of xt. Okay, so this is the second. The third conclusion is this xt has independent and stationary increments. And we know that for each t, xt has the law of Poisson random variable with intensity lambda times t. So the conclusion is these three statements are equivalent. So here we can see that the second one is the most easy to check. So this tells us in order to prove that xt is a Poisson process with intensity lambda, first we need to check it has independent increments. Second, we only need to calculate this to probability and see how it decreases as epsilon goes to 0. Okay, so these three statements are equivalent. So first, from 1 to 2, this is just immediate from the definition. So we know that if xt is a Poisson process, then xt plus epsilon minus xt equals 0. It means that the counting process between t and t plus epsilon equals 0. And we know that this counting process is a Poisson random variable with intensity lambda times epsilon. So the probability for this guy equals 0 is e to the power minus lambda epsilon. So of course, it decay like 1 minus lambda epsilon plus an error term. And the second probability is just tell us the counting process equals 1. So this counting process is a Poisson random variable. We know that the probability of it equals 1 equals lambda epsilon times e to the power minus lambda epsilon. So as epsilon goes to 0, we know that the decay like lambda times epsilon plus an error term. Okay, so from 1 to 2 is just emitted from the definition of Poisson process. And then from 2 to 3. So we already know that this process has independent increments. So independent increments. And now we will first show that xt has the right law, and then show that it has stationary increments. So first, we show that xt has the right law. So in order to show the law of xt, we need to calculate what's the probability for xt equals k. And I define this function of fkt. And the only thing we can do is to compare fkt to fkt plus epsilon, because this is the only condition we know from here. So compare fkt plus epsilon and fkt. So what is fkt plus epsilon? So it equals the probability that xt plus epsilon equals k. And then we divide this event according to what happens at xt. From the second property, so we have these two estimates. And we know that for this summation, when n equals k, the probability is almost 1. And for n equals k minus 1, the probability is lambda times epsilon. And for all other events, they are just the error term of epsilon. So we know that for n equals k, the probability is 1 minus lambda epsilon times plus an error term. And for n equals k minus 1, the probability is, oh, no. So I will write it explicitly. So for the probability of and for all other terms, we know that they are very small. So the only leading terms are the first two terms. For this guy, so it tells us xt equals k, and xt, and from t to t plus epsilon, there's no jump. And we also know that it has independent increments. So what happens for xt is independent of what happens from t to t plus epsilon. So this guy has the probability that xt equals k, and for the next epsilon interval, there's no jump. For no jump, we know that the probability is 1 minus lambda epsilon, and the plus an error term, so the error term will absorb in here. This is the first term. For the second term, we know that this is the probability of xt equals k minus 1, and there's one jump within the time length of epsilon, and the probability is lambda epsilon plus an error term. So this is the probability, and now we can compare what happens to fkt. So this, if we arrange this expression, so here, by definition, it equals fkt. And here, by definition, it equals fk minus 1t. So what we have proved is fk t plus epsilon equals fkt 1 minus lambda epsilon plus fk minus 1 t lambda epsilon plus an error term. So here we remove this term to the left-hand side. And here we can see that we can take derivative with respect to t. So now what we have is, if we take we divide the epsilon to both sides and let the epsilon goes to 0, this tells us the right limit equals the right derivative of this fk equals the right-hand side. And we can compare fk t minus epsilon and fkt similarly, and we can also show that the left derivative is also the right-hand side. So here, in fact, we can show that this fk is differentiable with respect to t, and the derivative is given by the left-hand side. Okay, so this is we are in a good shape because now we have an ODE, and the next step is to solve the sequence of the equations. Okay, so but we can't solve it directly because there's another function k minus 1. So we have to start from f0. So what happens to f0? A similar calculation will tell us f0t equals minus lambda f0t. So this is for k greater than 1. And when k equals 0, this is the relation of this calculation. So from here, we can already see that this f0t is exponential in t. And then we can prove by induction that fkt has this form, and this is exactly the form we want. So this tells us xt has the law of a Poisson random variable with intensity lambda t. So now we go from second to third. We have already, it is from the assumption that we have independent increments. And we just show that xt has the right law. The only remaining thing is we need to show that it has stationary increments. So we can apply the same analysis for xt plus s minus xs. And exactly the same calculation will tell us this random variable has the law of Poisson random variable with intensity lambda t. So this tells us x has stationary increments. So now we have completed proof from 2 to third. And now the final step, we have to go from third to 1. Okay, from third to the first. So now what we know is this process xt has independent stationary increments, and xt has the law of Poisson random variable with intensity lambda t. So in fact, the property for, in the third statement already tells us the any finite marginal loss So this property already tells us all the finite dimensional marginals of this process. So this is uniquely determines the process, and it has to be Poisson process. So we know that it has to be a Poisson process with intensity lambda. So this complete proof that these three statements are equivalent. And from here, we can say that in order to check one process is a Poisson process, we only need to check the second statement. So we only need to check it has independent increments, and we only need to calculate what is these two probabilities. Okay, so this is about Poisson process. Now we have a break.